Hi, folks. So we have talked about a couple things in chapter 2. We've talked about displacement and velocity and acceleration. And so now we're going to put some of those ideas together of displacement, velocity, and acceleration. And we're going to use them in something called the kinematic equations. So the variables in those equations are going to be, well, let's see, displacement, like I said, displacement, acceleration. And if we use these kinematic equations, we always have to keep in mind that our acceleration has to be constant in order for these equations to be valid. Let's see, what else? Final velocity, initial velocity, and elapsed time, delta t. All right. So here's our kinematic equations, and I'm not going to read these off to you, but these are very, very powerful tools when we're trying to analyze motion, and we've got a constant acceleration. And so we're going to use these a fair amount in chapter 2 and in chapter 3. All right. So there's a set of problem-solving steps when we're dealing with problems of motion that I would really highly advise that we follow and we get used to using. Excuse me. So the first thing we want to do is make a drawing. We need to decide on the positive and negative directions of motion. Now, typically, we'll just make to the right positive and upwards positive if we're moving up and down. Okay, what else? After that, we're going to make a table of values for those 5 kinematic variables that we had on the previous page, 2 pages ago. At that point, we're going to see if we've got 3 of those 5 variables. If we've got 3 of those 5 variables, then we can use those equations to figure out the other 2 unknowns. And then lastly, if we've got something that, say, maybe has different accelerations for parts of its journey, we've got to divide that journey up into segments so that we consider just one segment at a time when the acceleration is constant. So maybe we've got a runner that speeds up at an acceleration of 2 meters per second squared, and then the runner runs at constant speed after that. If that were the case, we would have to analyze those 2 segments that have different accelerations piece by piece individually. All right, so let's take a look at an example problem. In this example problem, we've got a skater that moves across ice at 8 meters per second. She hits a rough patch that's 5 meters wide, and as a result of that, she slows down to 6 meters per second by the time she finishes crossing the rough patch. We're asked for a couple things here. We're asked for her acceleration, and we're asked how long does it take her to cross. So what I'm going to do is I'm going to try and draw a picture. So let's see, there's my person. She's moving this way at 8 meters per second. And then she gets over here maybe, and now she has slowed down some. Notice the vector there is smaller. There we are. This is on a rough patch. And what's the length of the rough patch? It's 5 meters. All right, so that's my first step is just to draw that picture. All right. Should be, there we go. What's my next step? My next step is deciding on a positive direction. So we'll make to the right positive. And after that, I start writing down a table of values. So let's see if I can do that. My delta x, my displacement, is positive 5 meters. My initial velocity is 8 meters per second. My final velocity is 6 meters per second. I don't know the acceleration, and I also don't know the elapsed time. And those are the 2 things that I want to find. All right, so there's our table of values, and we see that we do have 3 of the 5 things. So now what? Well, now we think back to those kinematic equations that I had on the slide a couple slides ago, and we pick out one that might help us out. So let's try and solve for acceleration first. So we've got velocity we've got final velocity, we've got initial velocity, we've got displacement, and we want to solve for acceleration. So we've got final velocity, initial velocity, we've got displacement, we want to solve for acceleration. It looks like that one right there is going to be the one that probably is the most useful. Now, if I wanted to, I could solve for time first. I could solve for time. How could I do that? I could use maybe this one right here. That would certainly work. And that's the only one that would work of those choices. All right, so let's solve for acceleration first, though. All right, so here we go. We've got v squared is equal to v naught squared plus 2a delta x. And let's see, let's rearrange this guy. So subtract v naught squared from both sides. 2a times delta x. And then we're going to divide both sides by 2 delta x so that we can isolate a. So we end up with v squared minus v naught squared over 2 delta x is equal to a. And that looks very familiar, should look very familiar to you guys. That's one that we asked you to solve on that first worksheet that we had for lab. All right, so the initial velocity is 8 meters per second. Final velocity is 6. And then divided by 2, and then the displacement is 5. So divided by 2 times 5, and if we punch all that in the calculator, and I encourage you to do this, we should get out the result, negative 2.8 meters per second squared. All right, so her acceleration is actually to the left. This makes sense. If her velocity is to the right and she's slowing down, then the acceleration has to be pointed in the opposite direction. So velocity is to the right, acceleration's got to be to the left if she's slowing down. All right, so the next thing is to figure out our time. And in order to do that, I'm just going to use this equation right here. B is equal to V naught plus A delta T. All right, let's rearrange this guy and solve for delta T. And then we end up getting V minus V naught over A is equal to delta T. And so let's plug in some values there. Delta T is equal to 8 meters per second minus 6 meters per second divided by negative 2.8 meters per second squared. When we punch all that into a calculator, we get out the result that this is 0.714 seconds is how long it takes her to cross. All right, so that's an example problem, and we are going to do some more of these in class. So I look forward to that.